Alright, we are back, and we can now start to think a little bit about this problem. So I would like to start by doing a little bit of reasoning before we go through the steps. So first of all, when we have a system like this, is this a 2 degree of freedom system? Yes, it is, because we have two masses and their motion is independent from each other, because we can have the mass moving by a certain amount on the left or on the right, and then the motion of the other mass can be in any quantity on the left or on the right, again regardless of what's going on here. Of course, we have the spring connecting the two mass, so the two displacements are influenced by each other, but it's still a 2 degree of freedom system. It is also free because we don't have external forces, so at some point, in order to have motion, we will need initial conditions, either from velocity or displacement. So now I'm not going to go through like all the details of all the steps and all the calculations for this problem, because it will take a little bit too long. I would like to finish this by the end of this lecture, but I will go through the main steps at least. So we can start here. We are asked to find the equations of motion. So how do we find the equations of motion here? We can look at the free body diagram. In this case, the free body diagram of both masses is actually pretty simple, because they are both subjected to one force only, which is the force of the spring. Since we have only that force, since we only have that spring, actually the force is the same on both masses. So we can, from the free body diagram for the first mass, so free body diagram. So for the first mass m1, we have, let me two. So we have the force that comes from the spring, and then for the second mass we can have the force in the other direction. Of course, the force depends on what we assume to be the initial displacement of one mass with respect to the other one. So in this case, we have that the force of the spring would be equal to k times x2 minus x1, and then in this case is the same, F is equal to, k, that, so in this case let's do here, F is equal to k, x2 minus x1. So when we look at these two forces, we can write the equations of motion. Of course, summation of forces equal to mass times acceleration. So for the first mass, we have m1 x1 double dot minus k x2 minus x1 equal to 0, and for the second mass we have m2 x2 double dot plus k x2 minus x1 equal to 0. Of course, what we want is to write them in the matrix form. Before we write them in matrix form, it is convenient to reorganize all the variables. So again, we're gonna have the accelerations and the displacements. In this case, we can rearrange as follows. So we have m1 x1 double dot minus k x2 plus k x1. We could switch these two so that we have x1 first and then x2, but eventually it's the same equation. And then here we have m2 x2 double dot plus k x2 minus k x1 equal to 0. Again, of course, here we can switch. We can have x1 first and then x2 in terms of displacement. Same thing here. When we write, separately, doesn't really matter. Of course we have to keep this into account when we write them in matrix form, because when we write this in matrix form, this is how it looks like. M1, 0, 0, M2. So this is the mass matrix multiplied by the acceleration, x1 double dot, x2 double dot, plus the stiffness matrix, k, negative k, negative k, k. This multiplies the displacement vector, so x1 and x2 equal to 0 and 0. Make sense? So if you remember last time we said, okay, once we are here, once we write the equations of motion in matrix form, there is one thing that we need to check to make sure we are on the right track. Do you remember what we have to check? We have to check the symmetry, so we have to look at these two matrices and make sure that they are symmetric. M1, M2, 0, 0 on both sides, this is symmetric. Here we have on the principal diagonal k and k, and then above and below we have negative k and negative k. So both matrices are symmetric, so it looks like we are good to go. We can go to the next step. So now that we have the mass matrix and the stiffness matrix, what should we do now? If you look at your notes from the previous page, now we are asked to find the natural frequencies. And we can find the natural frequencies because to find the natural frequencies we need the mass matrix and the stiffness matrix. How do we find the natural frequencies from the mass matrix and the stiffness matrix? We simply look at the determinant of negative omega square m plus k equal to 0. Which means that we plug this matrix here, we plug this matrix here, which means we multiply this one by negative omega square, and then we add k, and then we calculate the determinant, and then we equate the determinant to 0. I'm going to skip all these algebraic steps, and the equation that we use to find natural frequencies would look like this. We have omega square, this multiplies m1 times m2 omega square plus negative m1k minus m2k equal to 0. Exactly like we had before, even in this case, we found an equation, an algebraic equation in omega that is of the fourth order. Because if we multiply this term by this term, we have omega to the power of 4, right? Which means that we have 4 solutions. Now, when we rewrite the equation in this way, we can quickly see that the first 2 solutions of this are actually plus or minus 0. Because if we take, of course, plus or minus 0 physically doesn't have meaning. So we talk about 0 because this term multiplied by this term equal to 0 means that in order to have this equal to 0, omega must be equal to 0. So our first natural frequency is equal to 0. The second natural frequency comes from equating this to 0. When we plug the numbers for mass and stiffness, we obtain that our omega 1, our omega 2 would be 16.73, and these are radians per second. Of course, we know that omega 1 is 0 and omega 2 is 16.73 because we said by convention that omega 2 must be greater than omega 1. So we actually already solved the first two questions because we found the equations of motion, and we actually wrote them also in matrix form, and then we also found already the natural frequencies. So please keep in mind that when we look at the natural frequencies of a multiple degree of freedom system, the motion of each mass in this case, or in general the motion of each degree of freedom, is a combination that comes from the two frequencies. So even if we have that one frequency is equal to 0, doesn't mean that the first mass has 0 frequency of oscillation, because the first mass oscillates oscillates with a motion that is actually a combination of these two frequencies. Also, the second mass oscillates at a certain motion with a certain motion that is actually a combination of these two frequencies. Makes sense? So the next step would be to find the two vectors u1 and u2. In order to find the two vectors u1 and u2, we can look at the following relation. We have so we have negative m omega square or negative omega square m plus k times u equal to 0. So we start with omega 1, which is equal to 0. We have negative m omega 1 squared plus k u1 equal to 0. So the fact that the frequency is actually equal to 0 in this case simplifies a little bit our system. And then what happens is that basically we will have the stiffness matrix that multiplies this vector and then equal to 0. Even in this case there are a few steps. This is actually pretty simple because it's just this times this equal to 0. So when we plug the numbers, we obtain the two components of our u1 vector. So even in this case we end up with two equations that are the exact same equation. So one of the two variables must be chosen arbitrarily, then we can calculate the second one. So in this case we obtain that the two components u11 u11 we can select equal to 1, and then u21 will be also equal to 1, which means that our vector u1 will be equal to 1 and 1. We can do the same with the second, natural frequency. In this case we have to go through the actual steps because we have we have the second natural frequency. And then even in this case we end up with two equations that are the same, so we can select the first one, the first element, and find the second one. In this case we will have that u11 we can select also, or actually sorry, u12 we put equal to 1, and then u22 will be equal to negative 1. Any questions so far? So now that we found our natural frequencies and our u vectors, we can actually start to look at the initial conditions. So we can write the initial conditions also in terms of vectors. So we'll have the initial position, which will be equal to 0 and 0.1, and the initial velocity x dot of 0, which is equal to 0, 0 in this case. Now, another thing that we should consider here is that since we found that the first frequency is equal to 0, the general form of the solution is actually slightly different from what we saw before. Again, remember that all these differential equations are solved by trial and error, pretty much. So this is the main difference with what we saw in the previous example, because in this case, the general form of the solution, again in vectorial form, would be like this. X of t is equal to c1 plus c2t times u1 plus a sine of omega 2t plus phi times u2. So in this case we didn't, as you can see, for this form of the equation we didn't use omega 1, because omega 1 was equal to 0, and then it means we would go back to, if this term was equal to 0, we would go back to a situation where we have only one degree of freedom, which we know that is not the case. So we still need to consider the fact that we have multiple degrees of freedom, in this case 2 degrees of freedom, and also we should consider the fact that the first frequency was equal to 0. So with this form, at this point the process is very similar to what we saw before, because we still have to find 4 constants, which are c1, c2, a and phi. We still have 4 initial conditions: position and velocity of the first mass, position and velocity of the second mass, so 4 in total. So we should do the exact same thing, which means we have to basically split this into 2 functions, which means we have x1 of t equal to c1 plus c2t times 1, which was the first component of the first vector u1, plus a sine of omega 2 t plus phi, also times 1, and then the second one, x2 of t equal to c1 plus c2t times 1 as well, plus a sine of omega 2t plus phi times negative 1, which was the second component of the second vector u. So at this point, again, I'm not going to go through all the derivatives and then the substitution, but again, the steps are the same. We have the 2 functions, we need to find the 2 derivatives, then we plug 0 for the time, and then we equate to whatever values we have for the initial conditions in terms of position and velocity. So once we go through all these steps, we can find that phi will be equal to pi over 2 then we have that C2 is actually equal to 0, then we have that A is equal to negative 0.05, and then the last constant, which was C1, is equal to 0.05. Again, we have all the steps in between. Now that we have these constants, we can finally plug them in the first and the second solution, and then what we obtain, again, after plugging, would be x1 of t equal to 0.05, and then this multiplies 1 minus cosine of 16 plus 73t. Remember, we have the second natural frequency, and then x2 equal to 0.05, and then 1 plus cosine of 16 plus 73t. Again, all the steps that I skipped here to find the two components of u1, u2, and then to find the constants are basically algebraic steps that are needed to basically find these results. But if we look at the overall process, is basically the same that we saw before, except what kind of solution we pick as a general solution, which is this one here. Makes sense? Any question? Okay, what I want to do now, since we have the last minute, I just want to give you another example that you can use to make practice. So let's assume we have this system here, and then we have two rods that are connected to each other through a certain spring. And then we can call this, the mass can be the same for the two, and then we can have the total length of the two rods equal to L, and then the distance between let's say the ceiling and the spring can be A for both of them. So we have A and then also A here. So in this case, again, you can make practice and you can find the equations of motion, and then you can find the natural frequencies, and then eventually you can find the solution of this, which means the displacement of the first mass, the displacement of the second mass. Any question? Alright, if there are no questions, I guess we are done for today. Thank you very much for being here today, and I will be here again next Wednesday to do the other lecture, if you can be here, of course you are more than welcome. Alright, thank you very much, and have a good night. Bye.